You might have heard the urban legend, will a near miss with a 50 BMG blow off your arm, or worse, will it kill you?
Today we're going to take some measurements and actually put some numbers to this and resolve this once and for all.
It's new, weekly updates from Ultimate Reloader. We're talking about free resources, exclusives, hot deals, and more. 3 ways to subscribe. Click on the button on the website. Go to ultimatereloader.com/subscribe or click on the QR code. Gavin Gear here from ultimatereloader.com. I'm joined by John Miller from DoItSoft. Thank you for joining me, man.
Yeah, thanks for having me out.
This is gonna be fun. Okay, so where does this myth come from? This urban legend?
Yeah, I think it comes from a long time ago. It was a military legend where you could basically miss your target, but it would still cause some damage. And then I think in the last decade, there's been some guys that have kind of revived this myth, if you will, and some guys that believe they've debunked this myth, but all of which has somewhat compelling evidence. So maybe let's go through some of the things we found.
Yep. So perhaps the best piece of evidence, if you want to think of it that way, was a video that Keith Warren Hunting published about 6 years ago. So let's watch this. This is a near miss on a doe with a 50 BMG, a Barrett.
And it does look compelling. So, you can see kind of a cloud of mist coming out from near the head of the doe. It obviously drops. And then I think later here, he shows like a close-up of the deer, and there's blood coming out of the eyes and the mouth.
Right.
And his claim is that he didn't hit the deer at all,
but that it sucked the eyeballs out.
That's
the exact verbiage that he uses.
That is the words he used.
Yes.
Yeah. So that's his story. And then there's other folks that have done kind of try to debunk this, but really lacking evidence, right?
Sure.
So
like this guy, right? He takes a 50 BMG, shoots close by a ballistics gel torso. Kind of not really the same thing, and it's more of this subjective, like, let's shoot by something and it didn't jiggle enough, or
right.
it didn't move enough, right? And that's different than actually putting numbers to things. But outside of YouTube, there's a whole bunch of discussion as well.
Too.
My friend still believes a 50 BMG will tear your arm off if it doesn't hit you, right?
Yep.
There's a bunch of discussion on that. Or can the concussion of a 50 caliber bullet from a sniper shot kill you even if the bullet misses? That's the exact myth right there.
Right, and there's all sorts of different variations of it. But the sad part is, like, there's a ton of PhDs, medical profession PhDs, that have done all sorts of research showing like what the governing factors would be in terms of an actual number that we can simply measure. Right.
Right.
So
and there's a progression there, right?
Yeah.
You're first going to feel something, right, on your skin.
Yes.
Then eventually, if there's enough pressure, like if you have a bomb go off nearby, right, your eardrums are going to rupture.
Usually that's the first failure mode.
All that, right? And then as you go further than that, the destruction gets worse, right? Maybe your eyes are susceptible.
That's kind of what I think it'd be. Ears would go first, then eyes, then you'd start getting tissue damage and things like that.
TBI, probably. Your brain's going to be
most likely,
jiggling around, and then eventually death. So we have a couple of scientific resources that you've investigated here, starting with hearing.
Yeah. So the hearing, I mean, if we can't cause hearing damage from whizzing a bullet by, then I would say this myth is busted.
Right.
So for rupturing an eardrum, it looks like, the way that I read this medical journal, it says, some damage can occur at about 5 PSI. Well, it's almost certain you'd have a ruptured eardrum at 14 PSI of a dynamic pressure change right by your ear.
Yep.
So that's kind of the first failure mode.
Okay, and then for your eyes?
Yeah, so for an eye, it says the rupture pressure for a human eye is about 0.9 plus or minus a third megapascals. So for reference, 0.9 is about 130 PSI. 1 megapascal is about 145 PSI. So what we have here is a pressure transducer that's embedded in this plate. It's a 100 PSI range.
Okay.
And we can start at 2 feet, maybe move to 1 foot, move to 6 inches, move to 3 inches, and we can build that pressure curve as we get closer and closer to the object.
So this will get us to the point where we can say, would eye rupture happen? Yes or no?
Would you blow out an eardrum? Would you rupture an eye?
Yep.
If you do both of those, then maybe we need to switch out a higher pressure range and make the same measurement to see, what other sort of tissue damage might occur.
Right, and this is going to be connected to this DAC module. This is a Sirius 8 channel.
Yep.
Which this is a recent upgrade we've had. We've used it a little bit. Look at our 6GT high pressure video. 200,000 samples per second.
Yep.
So really good time fidelity.
Yeah, so we make systems that go up to even 15 million samples per second, but for a pressure curve like this, 200,000 samples per second will be more than adequate to see a nice pressure curve as it goes
Works
by.
great for chamber pressure, right, which is a very rapid phenomenon, right? Okay, so the rifle that we're going to use, this is the 50 BMG build that we did on the channel. It's got a BAT EX action. It's got a 32-inch barrel. The Triple X Bastard brake does a really, really good job taming the recoil, but you definitely do feel the blast.
Sure, and maybe that's a good thing to do if we make this measurement and we don't find a lot of compelling evidence. Maybe we can move this and measure some blast pressure,
Right?
To see, is that worse or?
Sure.
Now, realistically, we should have like a pencil probe. Like PCB makes those pencil probes for that.
Yep.
But this would give us some really rough numbers in that regard.
Gotcha. For ammo, this is kind of your plain vanilla 50 BMG. I think this is a 680 grain projectile, belt-fed machine gun ammo. It looks like this was manufactured in 1952. And we'll grab some velocity data. Obviously, when you go over that supersonic threshold, the dynamics of pressure change. You have that pressure cone, right? Kind of like a compressed pressure region. And we're definitely going to hit that, but we'll put numbers to that as well.
We should certainly show that we're hitting that as part of this measurement, because that is critical.
Absolutely. Okay, so I just reassembled the rifle. This was a 375 Chi-Tac just this morning. So where we're going to start is getting this baby sighted in.
Sounds good. Let's go do it. Nice.
You're going to want to dry fire first.
Oh, okay.
Yep.
Nice.
2760. That's hauling. I'm going to go to the center target and finish the sight in. Takes one's breath away. Okay, I'm going to call that good. There's like smoke behind the building.
That shooting 6 rounds of those is like shooting 200 rounds of 223.
Oh, I forgot how abusive that is. So we got the rifle sighted in, and here we are at the target backstop from the behind shop 100-yard range. Let's talk about what we got going on here.
Okay, so I think the game plan is to have one of us shoot at like 24 inches from the center. And so here we can nicely see, what these distances are. So we'll shoot a nominal 24 inches, and then what we'll do is we'll look through basically the optics and figure out exactly, get it down to 1/8 of an inch or whatnot. I'll correct the distance. And so we'll do a shot at 24, a shot at 18, a shot at 12, a shot at 6. If we're shooting good, maybe we'll, venture to get a little closer. And then we'll build basically like an XY plot, building that pressure curve. And I can show you what we kind of have lined up over here. So here's the pressure transducer inside that box, and that's going to our data acquisition system. And then here's a little GUI that I built here where basically this is just showing the live pressure data. And then I'll start the calculation and stop it to just grab that max for that duration, so per shot. And then we'll type in the actual nominal distance and we'll plot that, and we'll build this pressure curve, which will obviously increase with pressure as you get closer to the sensing element. And the big question here is just, what is that going to be? Is that 100 PSI? Is that 5 PSI? Is that, what's the...
It's a sonic boom from a 50 BMG. It's going to be something, but what is it? We'll find out.
That's right.
Okay, so I'd say let's get set up at 100 yards and we'll start to collect some data.
Sounds good.
Here we go. That's 23.0.
23.0.
$17.5.
17.5. What do we got there?
12.
Okay.
That was 5.
Okay. All right, let's do one more.
Okay.
Close to 3 as you can get.
Yep. Let's go see what he's got.
What was that last number?
That was 3 on the nose.
3 on the nose. Okay.
Better?
It looks really good, actually. So maybe I should look at from this view real quick while it's populating on that X1. I changed the scaling, so I kind of messed it up. But here's where, let's send this to the back. So basically, these yellow marks are my notes, but these blue ticks are where you're scaling up.
Okay.
And so hopefully,
we zoom
in a couple of seconds, you'll see this build up.
Oh, wow.
So from 24 inches, we were roughly 1 PSI.
Okay.
18, we were 1 3/4. 12, we were maybe a little under 2. But at 5 inches, you were pretty close to 3 PSI.
Yeah.
And that last one at 3 inches was about almost 5 PSI. So from what we were looking at, the med journals,
yeah.
you're starting, and that was 3 inches. So getting a little bit closer, I would certainly believe causing hearing damage.
It was 4 to 14 was the overall range.
So 4 was like, or 5 was like where some people could start to get ruptured ears.
Gotcha.
And it was 14 was when almost everybody would. So we should do like exponential extrapolation there, and then come up with an actual number for as it approaches 0. But
that is pretty steep. So
it is pretty steep. But I think this one's not so steep. So when you actually average this out, it'll be
true.
Somewhere right around, to be honest, probably that 10 to 14.
To a fit curve kind of a thing.
Right, right.
So let's take a moment to peel back the curtain here and talk about this setup, because this is really amazing what this can do, right? In the past, for instance, with my prior recoil rig, I'd have multiple boxes, lots of cables, kind of a record, do whatever you're going to do, and then take all that data, a lot of which is going to be thrown away into external software, run an entire afternoon in Excel, and then what if you have to rerun the experiment, right?
Right.
Like this is a completely different level of capability. Why don't you talk about what we've got here?
Yeah, so from the hardware side, really what we do is we combine the functionality of your signal conditioning, your A to Ds. That's all in one box here, and then you're just supplying power. It can be battery power, wall power, and then communication cable back to the PC, and then just cables to those sensors. So jumping over to the software side, for instance, here I'm just setting up some analog input channels, and I'll plug in a sensor into channel 1 and not touch anything on the computer, and you'll see it'll automatically detect, I'm measuring, this is an accelerometer, here's my units, here's my sensitivity, and this turns green, showing it's drawing the right amount of power. So it's just kind of a plug-and-play system for the analog inputs. I can add video modules, so I can sync the video with my data. I can add like interactive buttons for when I want calculations to happen or things like that. And then I made some math channels here that took a couple of minutes before the measurement, just to make things look a little bit cuter. So this was the actual setup that we used for the test, where we could see the raw data. I could start and stop the calculation for each shot and then plot the point on this XY plot. And that's what we were kind of seeing, and that allowed us to just walk up to the end of the test, and you could actually see that pressure curve as we closed on the distance to the sensor. So we actually had the final result really done as we were walking up to that product.
Yeah, and that allowed us to see what was happening in real time. If the data doesn't look right, start over, all that.
Yep.
Yeah. And then ultimately you can just get a lot more done in a day, right? Less
Yep.
setup time, real-time monitoring of the results. Yeah, this is a total game changer for us.
Awesome.
Well, that was a fun experiment.
That was fun.
John and I just took a few minutes to kind of go over the data in depth and to just make sure that we had the appropriate filtering setup. Let's talk about the need to filter here, right?
Yeah.
The sensor itself has a resonant frequency.
Yep. Yeah. Every
It'll
sensor
vibrate at a particular frequency that it likes.
Right.
Yeah.
And I think maybe it's just easier to show that. So this is kind of the corrected curve, which we'll get to in a second here. But for each of these points, these are the actual shots of the bullet passing by this sensor. And really what you're seeing here is, so there's this high frequency component. And so with a lot of these sensors, it's really just like a diaphragm. And that diaphragm, it basically resonates at higher frequencies than what the sensor's capable of. Since we were measuring at 200 kilohertz, and the sensor is really not capable of keeping up with that, we were seeing some of those resonant frequencies, which kind of constructively add and destructively take away from the signal. So what you do is you look at the frequency of interest, and in this case, we applied a 10 kilohertz low-pass filter to track the actual pressure curve, which removes that high frequency or the resonant frequency component of the sensor.
And it also reduces the peak values.
It does reduce the peak value.
Yep. As you can clearly see here, the yellow is the filtered value.
Yep, and some people would have just taken this with the 10 or 20 kilohertz low-pass filter, and that would have been the raw data that they saw. We just happened to take the higher speed data, and so we could see that component.
Because then we can apply different factors to it and massage the data until it looks real, which it does here. Yep.
Exactly. So really what we're looking at here, so each of these peaks were correlating to a distance, and that was we could have used nominal distances, but I liked what we did where we shot. We actually would adjust it. We were off as much as an inch on some shots. So we would adjust that. We would write the actual known distance and then rerun and replot this data. And you can see it looks like kind of an exponential curve as it gets closer to, closer to the distance of 0.
Which makes sense.
Which makes total sense.
Yeah.
And after running that filter, I think even with running through some different regression curves and whatnot, it would be feasible to maybe reach that 4 to 5 psi as you're kind of infinitesimally getting closer.
4 on the low end, you may get some damage, and 14 on the high end. Yeah, your eardrum is ruptured. And let's walk through the values. So at 23 inches from the sensor, 0.5 psi, 17.5, 0.62, not much change there, obviously. You can see that's fairly flat on the graph. At 12 inches, 1 foot, 0.73 psi, 5 inches, 1.17 psi, and at 3 inches, 1.99. We'll call that 2 psi.
Agreed.
Yeah, and between 3 and 0, you're going to get to, scientifically, a scientist would argue, it asymptotically, approaches infinity, right? But we know that it's not real in this case.
Right.
You're going to get closer and closer and closer, and then eventually you're going to hit something, right? And we're saying, okay, we're not hitting it. That's the whole point of the myth, right? And so I agree. I think if you follow the fit curve here, it looks like it could peak around 4 psi. And that was where hearing damage, permanent hearing damage, rupturing eardrums can start on the lower edge.
So ultimately, to kind of come full circle on yay or nay on this, which I think we can call myth now.
Yep.
I think that you could make an argument somebody could potentially rupture an eardrum if it really passed through it. Maybe even just barely contacting the ear.
Yeah.
But in terms of popping an eyeball out, which would require 130 psi,
right,
there's just no chance.
So a 223 is not a 50 BMG, but we'd have to ask Trump what that felt like. Like that almost was the exact experiment.
That was pretty much the experiment.
Talking about.
Yeah.
But a 750 grain or a 680 grain projectile is definitely different than a 50 grain projectile. The entire dynamics around that shock wave. You're going to definitely hear it and possibly get some hearing damage. Your eyes are going to be fine. And you will live, right?
Yeah, I think that is the conclusion.
So there you go. That's the result. So, we know now that you're not going to die from a 50 BMG nearly missing your head. You may, but it's probably somewhat unlikely to have permanent hearing damage, like a ruptured eardrum.
Yep.
And that's it, right? So it's not nothing, but it's also not catastrophic. And it's really awesome to be able to put actual numbers to this data and the phenomenon as well, right?
Yeah, I mean, I think the discussion is resolved, and really the extent is potential ruptured eardrum, and that's it.
Yeah, and what I'm thinking is a natural extension of this that could be more ongoing work on my channel would be to take a look at muzzle blast dynamics. You know, we've already looked at recoil. I've had a lot of interest in, you know, muzzle rise dynamics with different compensator features and that sort of thing. It'd be really interesting to do sound level. We've already got significant traction there. We have the microphones. We have the DuaSoft plugin to calculate dB. All of that. If we could also quantify blast dynamics, I think that would be that would really round out that data set really nicely. And maybe get one of those PCB pencil probes like what they had at the SAMI conference.
Yep. Yeah, the pencil probe is really the right way to do that, and I definitely think that would add to your channel quite a bit.
Yep. So if you all want to see that kind of analysis and that kind of concrete data around how one muzzle device like a muzzle brake differs from another, drop a comment, or if there's other experiments or other myths that you're interested in, we'd love to discuss that with you. Thank you again, John, for coming.
Thank you. Thanks for having me.
This was super fun. More information about the products and the software and the sensors down in the article if you click on that first link in the video description. That concludes this video, and that means it's time to wrap it up. I hope you enjoyed this video. If you're watching Ultimate Reloader on TV and want to take advantage of free resources, exclusives, and hot deals, just hold your camera phone up to the QR code, tap on the link, fill out the information, boom, you're getting Ultimate Reloader emails. Don't forget to like and subscribe. Also, we're on Facebook, YouTube, Rumble, where we've got unrestricted content, and Instagram. Make sure to follow us on all those channels. Ultimate Reloader also has a commercial solutions division serving law enforcement, the military, and the gun industry. We have some unique capabilities, including a comprehensive suite of recoil testing and evaluation capabilities, trigger profiling, and more. Thanks again for watching.